to make sure. Can you see my full screen, or am I on the right screen?
We can see your full screen. It's good to go.
All right. Well, thanks again, everybody, for showing up. Kind of like last week, if you don't mind, I've probably got more slides than I can cover effectively in an hour. So just type in the question, and we'll answer them as we come. I decided this morning, I woke up a little bit early and I started thinking about my talk, so I changed a few things last minute. So bear with me. Hopefully it flows better than as it was. So today we're going to be discussing lime and liming. So here's what I'm going to try to get over. What pH is and how do we test for pH. We have a water pH or a salt pH. UK, we use the 1 molar KCl pH. A buffer pH. Here at UK, we use the Sikora buffer. We'll cover what how pH is important, why does it mean so much to us in a soil fertility program, how do we determine lime rates, and can we compare lab results? Like I said last week, if we have a soil test potassium value from Waters Lab, them using a Malic 3, we can compare that to UK. Lime's a little bit different. It depends on the tests they're using. And then determining lime rates also includes discussing the limestone quality. Then just getting down into the reaction, how do we neutralize soil acidity? We do that with lime and other products, and then some products that claim to do this will not. And then finally cover the application and some tools available. So soil pH, just a little academic here. What it is, it's a negative log of the hydrogen ion concentration. So really what we're looking at is the relative amount of H plus, that's the acidity, and OH minus in a solution. If they're balanced perfectly, that pH is 7 and we have a neutral solution. However, if we have more hydrogens than hydroxyls or the OHs, then its pH is going to be less than 7 and it's going to be acid. If it's 6.5, it's just barely acid compared to a pH of 1, which is a strong acid. But if it's less than 7, it's acid, and if it's greater than 7, it's alkaline or basic. So that means there's more hydroxyls floating around in the soil solution than the hydrogen ions. So what influences the soil pH really are a few things, but one of the things that people don't think about, and it really influences us in Kentucky, is the leaching of base cations. So base cation, calcium, magnesium, potassium, and sodium. So if we're leaching these cations out, they are taking a hydroxyl with them. So we see down here at the bottom, hopefully my pointer's showing up, I have a calcium and then a hydroxyl. It forms calcium hydroxide, and then that's leached. So we don't really leach the acid or the base by itself, but it's rather with a base cation. So in the southeastern US, we get more rain than evaporation. So we're leaching this hydroxyl, which is leaving acid or a hydrogen present, so it reduces our pH. If you go out west, they have alkaline soils. Well, they have less rain than evaporation, so these fertilizer salts will actually come from depth to the soil surface, bringing the hydroxyl with it. So hopefully that explains what's going on in the soil. So as I mentioned, the high rainfall leaching of soil bases. Also, natural rainfall is slightly acidic, somewhere around 5, I believe, but it has a little bit of acidity with it. So not only is it bringing acidity, but rather it's leaching these base cations, taking a hydroxyl with it. Then we have our clay minerals and soil organic matter. One of the big ones is aluminum. Aluminum 3+, it can donate 3 hydrogens as pH decreases. or it as it decreases pH as it donates the hydrogen. And then looking at soil organic matter, this is a carboxyl group, COOH. Well, certain situations, it can release a hydrogen and then reduce soil pH. Another method or mechanism that changes pH in our soils is the plants maintaining a charge balance. They like to maintain their current status. So if a plant takes up a cation, it's going to release a cation. For example, if a plant takes up 1 potassium, well, it's going to release a potassium or a hydrogen. If it takes up a calcium, that's a 2+, it's going to release 2 hydrogens. So just that plant maintain its own internal charge balance. By far, the largest influence on soil pH and production ag is the use of nitrogen fertilizer, specifically forms of ammonium. That NH4 plus is going to eventually convert to NO3 minus, so ammonium goes to the nitrate. It's going to release water and 2 hydrogen atoms. So this is what we do more than anything. Is that a bad thing? Well, that's just kind of the cost of doing business, but it's what we do. Corn, tobacco, any of these crops requiring a high nitrogen rate are going to reduce pH faster. So here's just some data that I got from Lloyd Murdoch when I started. It's funny, sometimes data gets a little dated. Sometimes 50 and 40-year-old data is just as good today as the day it was generated. This is some work that they did on the here on the station, but 5 years of continuous corn, how did that influence soil pH? They were starting pretty low, a pH of 5.3, but after 5 years of not adding nitrogen, it was pretty much about the same. It dropped a little bit. That's probably just sampling error. The bigger thing is they probably didn't get any yield by not adding any nitrogen. Adding 75 pounds per acre per year, dropped it to 4.8, and double that amount, it drops it to 4.6. So adding this nitrogen is decreasing soil pH, but we can deal with that. That's why we lime. Here's some data back in the mid-90s when I was working on my master's at, I was going to UT Knoxville, but this work was in Jackson, Tennessee. So we had several things going on. We had a no-till system and then a tilled system. We had no cover and vetch within each of those systems as a cover crop. And then we had 4 nitrogen rates, 0, 30, 60, and 90. So a few things that we can see. This is after 14 years of the same treatment being imposed. So with no nitrogen, or as nitrogen rates increased, our pH decreased. That occurred in every system, whether it be a no cover or vetch, or a tilled or no tilled. So increasing nitrogen rates decrease pH. That's given. We also see it going this way. Vetch is a legume cover crop. It's contributing what we've calculated was roughly about 65 pounds of nitrogen per acre. So when we have that vetch cover crop in, we're reducing pH. It's the same mechanism. That NH4 plus is nitrifying to nitrate, releasing hydrogen. So we see that in both. One thing we do see that the tilled system generally had a little bit higher pH value than the no-till system. And it was just mixing that through the soil profile a little bit, getting a greater distribution. So now we understand what can change it. So how do we determine soil pH? Soil pH is measuring the amount of active acidity present. We can do that with a water pH or a salt pH. And this is really just the immediate reaction. This is what is influencing the reactions in the soil. And I'll discuss water and salt pH a little bit more in detail in a minute. But then we have buffer pH. That's measuring the amount of acidity that's in reserve. So water pH is influencing the reaction. This buffer pH influences how long that reaction can maintain itself, or how long we need to, or how much lime we need to add to neutralize both the water or salt pH, that acidity, the active acidity, or the reserve acidity. So two different concepts, both related but pretty different. So why do we, and we being UK, why do we use a salt pH? Well, Frank Sikora noticed some seasonal fluctuations with pH over years and wanted to overcome that. So when we have a water pH, that can be influenced by the residual salt, fertilizer salts present in the soil, especially in a dry fall. So if we don't have these fertilizer salts leaching out, let's say we have a potassium, that potassium can bump or displace hydrogen off of the exchange complex. So we're actually kind of artificially elevating the amount of hydrogen that's in the solution that's being measured. So we get a lower pH than we would if we would have had normal rainfall. We can overcome that by just adding a set amount or a pretty high level of salt to reduce that seasonal variation. So we remove that variation by adding a known amount of salt. So we know how much salt we're adding, therefore we can measure it. And the relationship is water pH equals the salt pH. We use a 1 molar KCl or potassium chloride salt. So that salt pH times 0.91 plus 1.34 is what the water pH is. So don't get worried about this. This is what we do at UK. However, when you get the results back, they are they're expressed as a water pH. That's what everyone's used to looking at. That's what I'm used to looking at. So if I get research samples back and it's a salt pH, the first thing I do is convert it to a water pH, because that's the way I think. Same thing if we're talking about kilograms per hectare, I'm going to convert it over to pounds per acre or bushels per acre, so I have a good concept of what that value means. So this is what we do in the lab. So the buffer pH, again, we're measuring residual acidity. The Sikora buffer starts at a pH of 7.5. We add that after we take the water pH, and then it reacts with that residual acidity. And as it reacts with that residual acidity present, it reduces the pH of the Sikora buffer. And then you measure the pH of the Sikora buffer. The amount that buffer pH is reduced is related to the amount of residual acidity. And this is how we base our limestone rates. Different buffers decline at different rates. We used to use in Tennessee, they use the Adams-Evans buffer. I believe they've switched to a Sikora buffer now. We used to use a different buffer here until Frank replaced it with a Sikora buffer, but they start at different values. Waters Lab, I'm pretty sure they still use the Adams-Evans buffer, which starts at a pH of 8. So the point I'm trying to make, different buffers do decline at different rates, and they start at different pH values initially. So unlike looking at a Malic 3 phosphorus from Waters versus UK, it's not a direct comparison. So don't think, well, I'm going to take Waters pH and buffer pH and use AGR1 to calculate lime rates. It's not that straightforward. And I believe they still just use a water pH as well. So pH is a little different critter than P and K. So here's a little pictorial that I came up with to kind of discuss the difference between active and reserve acidity. Active acidity, I have this beaker, I know how much water is in it, or I know how much acidity is in it. We're going to use this for an example as water. If I suck this out with a straw, if this is a cup and not really a beaker, because you probably don't need to be drinking out of laboratory beakers, but anyway, this is a measuring cup I use to make cookies. I have 3.5 units of water in here. I drink this out. I know how much water I removed. I removed 3.5. However, if that is connected by a straw to another cup, this is your reserve acidity. So when I remove this 3.5 units of water, I have this much reserve acidity, or this much water that can move over and fill this cup again. Well, what we don't know about reserve acidity, if we just measure the pH of the soil, is how big this pool is. So do we have, less acidity or less water to replace that? Or does our pool look like this? So is it connected to a 12-ounce Coke can, or is it connected to a swimming pool or a bathtub? So this reserve acidity is a measurement of how much acidity. So we neutralize this acidity, this active acidity. Now we know how much reserve acidity can move over. So we need to not only neutralize this, but neutralize this reserve acidity. So that's what we're doing with this buffer pH. So talked around it, but haven't really said anything yet about why soil pH is so important. This is, in my mind, the most important soil property that we can measure. It influences more than anything else, any single property. If I was told I could analyze one component of a soil test, it'd be pH, buffer pH, phosphorus, potassium, magnesium, zinc, organic matter. If I could only pick one of those, the first thing I would pick would be pH, because that influences the nutrient availability and yield. In particular, phosphorus and the micronutrients are the big ones that come to mind. It also influences microbial activity, herbicide activity. So the triazine herbicides like atrazine and Princep, as your pH decreases, if you get much below 5.5, that activity decreases. On the flip side, your sulfonylurea herbicides, their persistent increases as pH gets more basic. So as pH goes above 7, we have these things hanging around. So some examples would be Classic, Harmony, Accent, some of your grass and sedge herbicides. So this is something, if you've ever seen me give a soil fertility talk, you've probably seen this slide. If you ever see me give a soil fertility talk in the future, you will probably see this slide, just to the simple fact of the importance of soil pH. It's considered the master variable, and it influences so much stuff. So we say our pH, we're looking somewhere around 5, at 6.4, 6.6, or 6.8, depending on the crops. But let's just take 6.5 and follow this line all the way down. The fatter this line, the more available it is, the more activity. So fungi, bacteria, nitrates, potassium. Well, calcium's kind of skinny here, but we catch phosphates, iron, it's pretty skinny here, that's a micronutrient. Magnesium, sulfur, manganese, molybdenum, zinc, copper, boron. So we catch the fat part of most of these things, and then we start looking at micronutrients, and even though it's not fat, or the fat part of the line, that availability is generally high enough in Kentucky if you can maintain your soil pH in the proper range. Another thing, I said phosphorus and your micronutrients. When we get a pH real high, we start interacting with calcium. So the calcium phosphates form, and they're not immediately available for plant uptake. We start getting into low pHs. We have aluminum and iron that start complexing phosphorus. So if we can be somewhere above 6 to 6.8, 6 to 6.5 is ideal. Generally, I don't get too worried about pH. If you're at 6 or 6.1, maybe even 5.9, you start getting down 5.7, 5.5, then you start running into these problems. The other thing with a low pH. Aluminum and manganese, even though they are used by the plant, when we start increasing their availability, they can cause root damage. So aluminum will ding up the roots, and once they're not properly formed, they reduce their function. So even though we can have adequate phosphorus or adequate magnesium or nitrogen available, maybe these roots aren't able to fully utilize them because they're not functioning 100% well. Another thing I said, micronutrients are needed in small amounts. So even though these are not the real fat parts of the line, they're usually available in sufficient quantities. Have alfalfa up here at 6.8. Molybdenum is a key component in photosynthesis. Uh, nitrate formation, the rhizobia. So I think that's part of the reason we recommend it a little bit higher. This molybdenum is really a key component in nitrogen fixation. So I said it influences nutrient availability. Here's another one for phosphorus. This is some work that I believe Murdoch worked with someone on it, but again, another slide that I got from him that was really pretty neat. Every year they added 80 pounds of P2O5 for 16 years. So after 4 years, 320, 640, 960, 1280. And they tried to maintain a pH difference. So this top line has a pH of 6.6. This bottom line has a pH of 6.2. We added the same amount of P2O5, or they added the same amount of P2O5 every year. What do we see? This pH of 6.6 always has a higher soil test value than the pH maintained at 6.2. So you get additional benefit out of your fertilizer if you maintain the correct soil pH. You can overcome a low pH by adding more phosphorus, but it makes your fertilizers more efficient. So this is just something he grabbed off of the internet from Penn State. That's talking about root function. The better root functions are seen at the higher pH. As pH decreases, we see less roots. And I was talking about these fibrous roots. See the fibrous roots here at 6.6, 6.4, 6.2, and then we get down to 4.7. They don't have that same ability to function. It's not the big thick roots. They'll take up water. It's these real small, fine root hairs that do the work. That's what's taking up your phosphorus. That's what's taking up your potassium. So these fine root hairs really influence the ability of a plant to function, the plant roots to function, take up nutrients. So another reason to lime. This is just straight up yield of different different soil pH values. As we increase, or as soil pH increased by about a half a unit every time, alfalfa yields increased 1 to 1.4 tons to 1.9 tons to 2.3 to 2.6. Crude protein generally increased along the same pattern. So alfalfa, again, we require or recommend a higher pH, 6.8, than we do the rest of our crops, and this is just indicative why. So here's corn pH. I've said several times we can overcome low pH with higher fertility, but we get a great benefit out of pH. So we had a soil pH of 5.2, so a low pH versus a 6.5. And within each of those within that soil pH, those two different ones, they had a high P and K level and a low P and K level. So low pH at a low P and K level, 100 bushels of corn. Now they added and they maintained it at a high level. Well, we bumped that up to 145. So roughly a 45 bushel gain by adding a lot of fertilizer at a low pH. However, look at this 5.2 in the low fertility versus the 6.5 in the low fertility. Got an additional 26 bushels just by adjusting the pH at this low fertility status. And then go on and maintain the pH and the high. Now we're back up here to a higher pH. So fertility and pH, they interact, they complement each other. Take care of both of them, they're going to take care of you better. So instead of herbicide activity, this was some work that was done at Spindletop Farm several years ago. They were looking at different pH levels. And the interesting thing was they were spraying the whole field with atrazine. However, you can see this grass behind, they were only liming these plots. They'd lime these plots for 10 or 15 years, but they weren't liming the alleys between the plots. Same amount of fertilizer, or I'm sorry, atrazine was going down. However, the pH in these alleys was lower, just had, you know, pitiful atrazine activity, not good weed control, just simply due to the pH. So what's our optimal pH? If you keep it somewhere around 6.5, and we'll be honest to you, you're good. If you're above 6.2 for most crops, you're pretty good. Might want to consider liming. But what our official recommendations say is 6.4 for pretty much everything we grow, row crop wise, grass wise, except for tobacco. And then if we're growing tobacco, they're going to recommend a 6.6 pH. And if we're growing alfalfa or alfalfa mix, a pH of 6.8. That comes back to that molybdenum availability, I believe. But again, if we're somewhere around 6.5, you're going to be in pretty good shape. Now, for your hort people on here, I know blueberries, azaleas, a few different crops require a pH, acidic pH. Generally, in the row crop system, I'm going the other way. So I apologize. Maybe we can touch on that later on, but this is what the majority of the row crops in production ag are looking at. So how does the liming reaction work? We have calcium carbonate. This is the example I use. You can have different carbonate forms, different silicate forms, or oxide or hydroxide, but by far the calcium carbonate is the most common liming material used worldwide. So that calcium will come dissociate. We have our carbonic acid formed. I'm sorry, here's your carbon dioxide or carbonate. It will form carbonic acid. It's, if you see CO3, it's grabbing 2 hydrogen, carbonic acid, that's going to dissociate to form water and carbon dioxide. So we removed these acid protons from the soil with the carbonate, not the calcium. Then the calcium goes on to replace that hydrogen that's been removed. So that's what's going on in a liming reaction, but how do we know the amount of lime that needs to be added? Goes back to what I talked about last week, a representative soil sample. We need to make sure that soil sample is truly identifying that area of interest. So we're going to assume we have a representative soil sample. Then that lime rate is going to be determined by what crop we're growing. So what soil pH are we targeting? And then it comes into play our water pH that was measured, or our salt pH, which is measuring again that active acidity, and then our buffer pH using the Sikora buffer. So that reserve acidity, we're again starting at 7.5, and it declines based on how much acidity is in reserve. So just the same concept, showing you again, we want to know how big that pool is. So we determined what our lime rate is. This is what, you won't see this on your printout, but this is exactly how it's calculated. If you want to look at AGR1 sometime, or if you, some reason or another, didn't, you put in a pH of 6.4, but you actually need a target pH of 6.8, you can go to AGR1, take your water pH, take your buffer pH, look them up, and it will tell you what the target pH. It'll tell you the amount of limestone to hit that particular target pH. So this example is just for corn. I had a water pH of 5.5, a buffer pH of 6.5. My target pH is 6.4. So I just looked that up in AGR1. It says, hey, I need 2 tons of 100% effective lime. So we're not using 100% effective lime ever. Well, very seldom in the ag field are we going to get R&V of 100. It's going to be lower. Probably the average R&V for lime across Kentucky is going to be somewhere around 0.67. So this is what I use, and I'll show you how you can be more specific than that. But kind of like calculating how much nitrogen do I need if I'm using ammonium nitrate versus urea. You take your rate, you divide it by that percentage. So in one, it's 67% effective. So 2 tons divided by 0.67, just like we would have done that fertilizer calculation last week, that works out to 3 tons of actual limestone coming from a quarry with the R&V of 0.67. So that 2-ton rate is 100% effective. What we actually have to apply using this lime is 3 tons per acre. And this is just a screenshot from AGR1, my 6.5, my 5.5, there's my 2-ton rate. So what influences the limestone rates? Again, what our target pH, and that's dictated by the crop we're growing, the amount of active acidity, the amount of reserve acidity, and that's determined by clay and organic matter, or influenced. So, well, that both of those influence CEC. Shouldn't I take CEC into account when determining my lime rate? No, because that measurement right here, the Sikora buffer, is actually accounting for CEC. The different pools of this reserve acidity are a direct relationship or directly influenced by your CEC. So really, we don't need to worry about CEC because the Sikora buffer takes care of that. So our target pH, the amount of active acidity, the amount of reserve acidity, and then the quality of our limestone. All that goes into determining how much lime we need to tell the client to spread to effectively neutralize our acidity. So what goes into lime quality? Well, it is 2 things. The first one is the purity, the carbonate, calcium carbonate equivalent. So, for example, a good rock might be 90% calcium carbonate. So if it's 90% pure, that means in a ton of lime, 2,000 pounds of lime, I have 1,800 pounds of neutralizing material. Or if I have something that's not quite as pure, has more impurities, less calcium carbonate, and that same ton of lime, now I only have 1,400 pounds of neutralizing material. So this talks about the purity, but then it also comes into the fineness of the grind. How fine is that limestone ground? So particle size determines the lime reactivity. The smaller it is, so these are mesh, this is a particle size as described by mesh, sieves. So 4 means there's 4 holes per linear inch. 20 holes per linear inch, and 100 means 100 holes per linear inch. So this is really fine material, and this is more coarse. So not quite a 1/4 inch, but this is pretty good size stuff. This would be maybe big, a little bit bigger than dense grade material you'd put in a driveway or something. So the amount of lime reacted in a 3-year period is influenced by the particle size. There's a little bit of reactivity going on with this coarse material, but very little. The more fine it is, the more it reacts. So I said the purity and then the particle size, that comes in, the purity and the quality comes in to come up with the relative neutralizing value. This is just looking at another example of fineness, how fineness matters. So if I have a 1-inch square of limestone, it comes down to surface area. There's 1 inch here, 1 inch here. There's 6 sides to a square, so I have 6 square inches of surface area with this 1-inch cube. Now, if I just take a knife or a saw or somewhere or another, I split this 1-inch square. I split it this way and then this way to make now 8 1/4-inch squares. I doubled. I cut it in half twice, but I quadrupled my surface area. So it's this surface area that's reacting with the soil to change the pH. So if we keep doing that, keep slicing this, when we get 1 cubic inch of limestone to pass 100 mesh screen, we would have approximately 60,000 square inches of surface area. So this block, if you keep splitting it enough, it goes from 6 inches of surface area, reactive limestone, to 60,000. So that particle size has a huge influence on the ability of that limestone to react and neutralize soil pH. What we say in Kentucky and most of the surrounding states are going to be similar, maybe not exactly the same. If it does not pass a 10 mesh screen, we're going to give it very little value. Or actually, we give it no value. It has some value, but very little. If it passes a 10 but not a 50 mesh screen, half of it's going to be reactive in 3 to 4 years. And what passes that 100 mesh or 50 mesh screen is considered 100% active. So this comes into our relative neutralizing value of R or RNV. That calcium carbonate equivalent, how pure is that? Is it 90% pure? Is it 70% pure? The fineness, so how much of it passes a 50 and how much is between the 10 and 50. So our RNV is our calcium carbonate equivalent, our purity, divided by that passing the 50 mesh screen plus half of it passing that 10%, that 10 mesh screen, but not the 50. So that's how our number's calculated. So now that we've calculated our R and V, what kind of different sources can we use to neutralize acidity? By far the most common liming material worldwide is calcitic limestone, calcium carbonate, CaCO3. If you get enough magnesium present, I think it's about 10% of the lime being magnesium. Then you have dolomitic limestone. But either way, the reaction is this carbonate, calcium or calcium magnesium carbonate, plus the hydrogen. Here's your acidity. Again, it's going to form this carbonic acid, dissociate to form water, CO2. Your CO2 is going to go up. So we consume this hydrogen. It was formed, it was contained in water. It's out of solution. So now we increase the soil pH. Different liming sources that we can use, very less commonly used, but calcium oxide. This has, if pure calcium carbonate with the proper grind has a R&V of 100, this is going to be about 130, 140. This oxide will reduce a lot more hydrogen than the carbonate. However, this is really caustic. It can hurt you if you get it on you. It's hard to deal with. It's a powder. It's not going to be used very often. Hydrated lime, it's it has hydroxyls. It's more reactive than the calcitic lime. Again, not as easy to use, but easier to use, safer to use than the calcium hydroxide or calcium oxide. Pelletized lime, all that is calcium carbonate. It's a lot of the fines bound together. And then waste products, some biosolids. If you have lime treated biosolids, one of the things they'll do, they'll treat the human waste with this calcium oxide or calcium hydroxide, get the pH up above, I believe it has to be above 12 for so many hours. So that's killing these harmful pathogens and harmful critters in the biosolids. Do that long enough, and then it has killed that. It's made these biosolids safe to use, but you still have a material that has a pretty high pH. So biosolids can generate, lime treated biosolids are a good source. Paper waste, that's a very alkaline. One of the first things ever used to neutralize acidity were seashells, these carbonates. And then wood ash. If you're in an area where they're growing a lot of, say, dark fired tobacco, spread those wood ashes out on your pasture or somewhere, because that has a tremendous liming availability or ability. But you got to be careful with that wood ash. You can get your pH way higher than you can with calcium carbonate. The highest you can do it in the soil with calcium carbonate is about an 8.2, and that's really hard to do. However, with wood ash, you can get it higher than that quicker. Gypsum. People think, oh, it's the calcium that's doing it. Gypsum is calcium sulfate, CaSO4. If we look at our reaction, we have calcium sulfate. Here's our acidity. Calcium is going to dissociate to form the sulfate. We still have our water. We still have our acidity. If you say, well, you can make hydrogen sulfuric acid. Sulfuric acid is H2SO4. So we're doing something. We're consuming that hydrogen. It's a strong acid. As soon as it forms, it's going to dissociate. So we're not taking this hydrogen out of solution like we are with the limestone. This hydrogen here is now in water. This hydrogen here is still free hydrogen, still contributing to acidity. So don't let anyone tell you that gypsum is going to change your soil pH because it has calcium. I used to use the slides, and I was working on it this morning. I said, oh, there's 2 misconceptions of lime. Well, there's more than that, but I thought I better discuss the calcium a little bit more detail. So the first misconception of lime is pelletized limestone is so much better and so much faster reacting than ag lime. It's a quick fix. Well, that's not necessarily true. It costs a lot more. It's easier to spread in certain situations, and you can use it in other situations where you might not be able to get ag lime in, but it is not better and faster than ag lime. Liquid lime is much better than ag lime. You can adjust the soil pH with a fraction of the amount of ag lime. So I'm going to spread 2 gallons of liquid calcium hydroxide and get the same effect as I do with 2 tons of ag lime. Not going to happen. And then this third misconception is calcium is what's neutralizing the soil pH. I've gone over that, just in the previous slide, but again, this is really important. Here's your hydrogen. Now here's your hydrogen. Here is your hydrogen with gypsum. You still have it. So with this calcium carbonate, it's contained in the water. It's taken out of the soil solution in the water. In this calcium sulfate or gypsum reaction, your hydrogen remains in the soil solution. And something I'm hearing more Josh is telling me about, we hearing it more towards the bluegrass, but this uh, outfit is selling calcium chloride as a liming material, saying how effective it is, and you can just apply 1 or 2 acre or gallons per acre, and it does it. Well, there's no carbonate, there's no hydroxide, there's no oxide, there's no silicate. Calcium chloride is not going to reduce pH. As I said, you can form sulfuric acid with taking this H and combining it with the sulfur. Well, if I combine hydrogen with chloride, what do I get? Hydrogen chloride, HCl, that's another strong acid. So it's going to dissociate. So it's not the calcium, it's these oxides and hydroxides. So the pelletized lime, and I need to boogie on, we're taking a lot of the fines in ground limestone. Now they will use generally a higher quality lime. You have your high CCE, high calcium carbonate equivalent, a more pure lime, grind it up fine, and then take that and use some sort of bonding agent to make a pell or a pellet. Lignosulfonates are one of the most common. It's a high quality lime. It has a high CEC or CCE and a high cost. You could easily look at $250, $300 per ton of pelletized lime, where I can get a ton of ag lime spread for $20. I talked to the farm crew this morning. They're spreading lime. $21 an acre is what we're spreading it for, or that's what it's being spread for. So $21 an acre spread versus $300 an acre, and you get to spread it. It's usually not going to be faster because you have to break down this lignosulfonate bond, and that's going to take time. And then another thing, how good of a coverage am I getting? If I have, if I look at this sheet and I'm going to say every word here is getting hit with a piece of ag lime, whether it be a fine or a coarse, I'm getting pretty good coverage over this. Now, if I look at this same spreadsheet or this same slide, and I'm going to say only the O's on only the letter O receives a piece of pelletized lime. Let's see, there's one, here's one, here's one, here's one. So instead of all these words, there's what, 10 words here? So I would have maybe 50 pieces of ag lime covering this area with the same amount of pelletized lime because it's in a larger form. 1, 2, 3, 4, 5. I get 5 pieces of pelletized lime. So it's not getting the same coverage, and then it has to break down. So I like to use the analogy of ice. I know I used ice the other day, but if you have one of these fancy refrigerators and you can either get whole pieces, whole cubes of ice, and throw that out there, let that represent your ag lime, you get a whole cup of ice cubes and throw it out on the ground, watch it melt. Take that same, put it on your crushed ice feature, get the exact same amount of ice, throw it on the same area of ground, let's say a 3 square foot, which one's going to melt faster, which one's going to have better coverage. So that's my take on pelletized lime. I hope that makes sense. Liquid lime, these were things that were brought to me over the years. I saw them on the internet, but one of the claims is 1 gallon of liquid lime is equivalent to 1,340 pounds of ag lime. Another 3 gallons of liquid lime was the same as 5,000 pounds of ag lime, or 2.5 gallons of liquid lime increases pH of 0.6 units. And then they kind of specified the top ½ inch. Yeah, I'm not even going to address that. That's kind of silly. But these here, let's just look at some math. So what is liquid lime? A true liquid lime, not calcium chloride, but true liquid lime is about 50% lime. Calcium probably going to be calcium, well, it's not going to probably, it's going to be calcium carbonate. Well, about 50% of that jug is going to be water. You have to put it in suspension. Well, to help hold it in suspension, it's going to be about 2% clay. So half of it's lime, half of it's water and clay. It is going to be a high quality material, finely ground, high R&V. It's going to have a fast reaction because it's finely ground. So it's going to change a little bit faster than ag lime because you have all the fines, whereas the coarser material is going to break down over time, so you have longer duration of change. So I know everyone likes doing math early in the morning, but math just really dispels this truth. So we'll use that first example. 1 gallon of liquid lime is equivalent to 1,340 pounds of ag lime. So I'm going to say that liquid lime weighs 16 pounds per gallon. That's including the water and the clay. And that came off of their MSDS sheet. That's their number. We're going to assume the average ag lime has an R&V of 67. That's going to not be far. And we're going to say that at 100% R&V, so if we convert this over 1 ton, that means I have 900 pounds of liming ability at 100% R&V. So 900 divided by 16, because it's 16 gallons, that means that this has to be 56 times stronger than the ag lime to 1 gallon to equal that. So the liquid lime, the R&V would have to be 5,625. And I assumed all of this 16 pounds was lime. Actually, only half of it is. So it would be more like 11,000 pounds. So if we went with this number, we need 56 gallons of liquid lime to equal this 1 ton of 67% effective ag lime, or actually about 112 gallons. And they do make good high quality liquid lime. There's just not many people around that spread it. So there is some truth to liquid lime, but don't let the gallon or 2 gallon fool you. You can't change the chemistry. I'm getting close to time. One of the things, the calcium magnesium ratio, they say too much magnesium can cause compaction. Magnesium high levels can disperse the soil, so it doesn't flocculate, it's not in clumps, it's just single particles. Then they kind of, when it rains, they'll fill these soil pores and more or less create compaction in a sense and reduce water infiltration. We can make that happen in the lab with pure magnesium, but it's almost impossible to do it in field situations. You wouldn't be doing it with limestone. You would be doing it with something like tons of Epsom salt, something that contains magnesium and not calcium. So it's just not going to happen. And we'll skip across this. So incorporating versus surface applying. When we're in a no-till system, our nitrogen or acid forming fertilizers are at the surface. We're going to acidify the top 2 to 3 inches. When we're applying lime, it's going to be effective because we're applying it where we're acidifying. Some work that Grove did back 20 or 40 years ago, 30 years ago. If it's really, really low, you're probably going to benefit from incorporation, but hopefully we don't let our pH get down to 4.5. I saw the same thing with my stuff in nitrogen in Tennessee, and I didn't get into it, but aluminum is one of the things causing your pH. So we're getting rid of the aluminum. We might not be changing the pH immediately, but we're helping out. So we looked at the half rate of lime versus the full rate of lime and the different scenarios. We didn't get quite the same change with the no-till that we did with the tilled. In the half rate, as pH increased, we did get a change, but not as much. Now here's our full rate. Again, a little bit better in the tilled, but we got down pretty low. This pH right here of 5.3, that was a 4.5 or a 4.7. It was really low. We shouldn't have let it get down that low. Hopefully most producers won't. We'll switch over and finish up. So some online information. Frank Sikora's done a real good job. I did not click on these. I think they're still, the links are still active, but economic lime, so the calculator that calculates what your lime rate is. If you submit it to AGR1, it's going to give you the number. However, if, you know, okay, well, I was going to grow corn, but now we're going to grow alfalfa. You can plug it in, or you can go to AGR1. There's economic lime 2 calculator. Now we can compare lime, different sources, different rates, and it can be found. And then the lime quarry results, sample twice a year. To me, that's one of the most beneficial pieces of information you can have. Here's the first calculator, the second calculator. Here's what I want you to see. This is just a screenshot I took this morning. Go to the regulatory services, and it shows you what the results are. So the last one was the fall of 2019. Should be getting the spring 2020 out anytime now. Gives you the most current sample for the quarries that sell lime in Kentucky. Very good. So this is just an example. Took a screenshot. This was, so we have Adair, Allen, Anderson, and Ballard County. We look at when it was sampled, the calcium carbonate equivalent, that's the purity, how much past a 10 mesh sieve, how much past a 40, and then here's our R and V. Again, purity times fineness. So this here has a R&V of 68. Well, if I could get the same, I know these counties aren't next to each other, but if I could get this R&V of 81 for a similar price as this, well, this would be the better deal. It's better material. So you can play with this as you move on. So just to wrap it up, in my mind, pH is the master variable. It is so important in the soil fertility program. We are the major contributors to acidity by adding nitrogen fertilizer. That's just the cost of doing business. It influences nutrient availability and herbicide activity. Both essential and toxic nutrients can be influenced by that pH. Go too high with one pH and it becomes, or one nutrient, and it can be toxic, or go too low and it could be unavailable. So it's one of the cheapest amendments you can add in your soil fertility, and you're looking for lime, not calcium. Don't expect it to change overnight. It takes a little bit of time. Really, anytime you can spread lime is anytime you can get over that field, not cause damage. One of the things you need to be aware of is compaction. The lime truck's pretty heavy. Calculate the cost per R&V, not the cost per ton. And then the soil test is such a good investment for your time and money. So that's what I've got for now. I'm sorry I went a little bit long, but I'm able to talk, answer some questions, and happy to do so. So let's see. Are there any questions? And I'm not seeing my chat screen. More, make share, pause.
There's we can start with one from Carol Hinton. Haven't searched very hard, but could this training be offered to producers for their cap requirement?
I would think so. I mean, I don't approve that. I think that's GOAP, but I know some people there, and I think they're pretty conducive to having different mechanisms. Just need to approach them and talk to them and see if they will accept that. And if you'll shoot me an email, I don't mind trying to start that out. It will take someone else to probably make it happen, like Craig or whatever, just to say where this stuff is being reported, who can view it and all that. But I I don't see why not. But I can't answer that. I can ask the question. Eric Baker, there's been some variability with quarry lime quality reports. Is regulatory services coordinating the lime quality testing now, or is it Kentucky Department of Ag? So, to the best of my understanding, regulatory services is doing that test now. They don't offer it to the public, but Frank is, I don't know if Frank's on here or not. If he is, he could speak to this a little bit better than I do. But I understand that our regulatory services are the ones collecting the sample, running it to the lab, and then posting it on the regulatory services page. That isn't KDA anymore, or at least the testing is not. We've reported it here for a long time. Have you all determined where these recordings will be located for rewatching? Hey, Kevin.
That one's for me. Yes, we are uploading them to our Ag Programs YouTube, and then the links to those are being put on the ANR's homepage. However, I can't upload anything longer than 20 minutes from home, and I only go to campus on Thursdays from 8 to 11, so I can't upload anything until Thursdays.
Okay. And I, after the last session, I mentioned this little coffee cats thing that I'm trying to get started. I started 5 little videos. I got one made just recording on PowerPoint. I don't have it posted yet. Lori Rogers, the coordinator for cats, has been home with her 3 kids. Her husband works some strange hours, so she hasn't been coming in, but we are trying to get that. I am going to warn you, it's not going to be super high quality. It's going to be me sitting and doing this same thing, but I think it will be really useful information. The one that I have that I probably one of the first ones is just how to read a soil or a fertilizer label. So I hope to put some of these little snippets on the CAT's webpage, which will be coming hopefully this week. And I don't know about credit for that. I doubt it. It's more intended to be just a real quick learning exercise. I'm not seeing any more questions. You guys have any more questions? Or like I suggested last week, if there's some things that you think would be useful to be covered, I'm happy to do that. I don't mind trying to do these sessions kind of set up a regular time. Yet today and last week worked out pretty good. As soon as I leave here, we're probably going out to the field to start marking and planting. But after we get the big rush done as far as getting things in the field, I am happy to do this again. Please let me know if this kind of stuff is useful. I enjoy doing it. I can reach so many people sitting here, and hopefully it's good information that you can use, but it would be better information if I know it's addressing your particular needs. So just let me know what you think, and email me, put something in there where I can, future trainings or something in the title line, and I'll try to get back to this, and maybe we can come up with something where we meet maybe once a month or something. This time seemed to work pretty well for people, but anyway, any questions or comments, I'm happy to address, and if not, future training for backyard gardeners. So kind of like a master gardener on this. Yeah, we can probably do that, or I know we can do that. We can boil it down to an hour. The little videos, if you look, and sorry I was running behind today. If you look at last week's recording, there's Kentucky Ag Training School, the CATS page. If you click on that link, that's where we're going to that's where we're going to post it. There's already current things there. If you look at the library, there'll be little snippets of presentations that we've given at different CATS trainings, but we will have it listed at the top instead of library. It should be on that same line and have coffee CATS. So that's where we hope to have it. Anything else? Well, if you guys don't have anything else, I'm going to start putting some flags in the ground and getting some potash applied so I can plant some corn.
Well, thanks everybody. And Edwin, there were 56 this time, minus you and me, so 54.
56. Well, thank you so much, and thank everybody for attending.
All right, bye.
Bye.